record your talk.
All right.
Yeah. So, okay. So, welcome everybody. Our guest speaker is Antony Valentini, Theoretical Physics, Imperial College London, and the title of his talk is Beyond the Born Rule in Quantum Gravity. Please, Antony, you can begin. The audience is yours.
Thank you so much. Is the volume all right? Can people hear me?
Yes, if you could a little bit increase your volume.
Increase my volume.
A little bit, yeah.
Let's see. Is that better?
It's okay. I think it's okay.
Is that good?
Yeah, sounds
All
good.
right.
Yeah.
All right. Well, my subject is Beyond the Born Rule in Quantum Gravity. And let me just quick little pre-comment, as it were. When I say quantum gravity, what do I mean? So we're going to be considering canonical quantum gravity. I'll be using the metric representation. We're thinking about quantizing the 3 metric on a space-like hypersurface. As well known, you obtain a Wheeler-DeWitt equation for a timeless wave functional. It's not perturbatively renormalizable, but perhaps it's valid in some approximation, perhaps not too close to the Planck scale. In any case, I'll mostly consider models of quantum cosmology with a small finite number of degrees of freedom. But anyway, with these limitations, I think we might still learn something. In particular, I'm interested in possible implications for the Born rule. So let me just summarize the main points of this talk. My first claim or suggestion is that there is no such thing as the Born rule in quantum gravity. The second point is that the Born rule emerges only in a semi-classical regime by a process of quantum relaxation on a classical background. The third point, which is a bit more speculative, is that quantum gravity corrections to the semi-classical regime can make the Born rule unstable. Now, perhaps it's a good point to say, I think the first 2 points in my argument are quite strong, assuming canonical quantum gravity and assuming the de Broglie-Bohm formulation of quantum mechanics. The third point depends a little bit on something that it is open to question, as I'll describe. All right, so the main points, just a little bit more detail. When I say no such thing as the Born rule in quantum gravity, I mean that the modulus of psi squared is not a probability. And when I say that the Born rule emerges only in a semi-classical regime, what I mean is if we imagine a regime where, for example, you have some fields propagating on some quantum fields propagating on a classical space-time background, then in some approximation, you obtain a time-dependent Schrödinger equation for those quantum fields. In that regime, where you're basically doing quantum field theory on a classical curved space-time, in that regime, psi squared can be a probability, where psi is now the effective wave function for this quantum system. And when I say quantum gravity corrections can make the Born rule unstable, I mean that if you have an initial ensemble that obeys the Born rule, it can evolve to an ensemble where the Born rule is violated. So let me move on. When I say there's no such thing as the Born rule in quantum gravity, so again, we're looking at the Wheeler-DeWitt equation. Why would I claim that the I've got till 11. Okay. Why would I claim that psi squared is not a probability? Well, the essential reason is that, as is well known, the solutions to the Wheeler-DeWitt equation are not normalizable. And the essential reason they're not normalizable is because mathematically the structure of the Wheeler-DeWitt equation is like a Klein-Gordon equation on space-time. So you've got the Wheeler-DeWitt equation on an infinite dimensional superspace. Mathematically, it's comparable to a Klein-Gordon equation on four-dimensional space-time. Now, this the Wheeler-DeWitt metric on superspace is indefinite. So what this means is if I try to integrate mod psi squared over the whole of superspace, it's going to diverge just as the integral. If I take a solution of the Klein-Gordon equation, I integrate psi squared over the whole of space-time, it will diverge. Now, one might worry here and say, well, hang on, this integral on the left-hand side, you're integrating over three metrics. There's a gauge volume, a coordinate volume. There's a continuous infinity of degrees of freedom. Maybe the divergence has got something to do with that, and we can remove it. I think those are distractions and are not really the point. As one can illustrate, I think the essential point is that in effect, you have a wave-like propagation on superspace. So we can illustrate this with a model of quantum cosmology where there's no issue of gauge volume, you have a finite number of degrees of freedom. So we take a simple example of an expanding universe, flat expanding universe with a scale factor, contains a homogeneous matter field with a potential. Now the Wheeler-DeWitt equation for this model looks like this. And if you write it in terms of alpha equals the log of the scale factor, you get indeed a two-dimensional Klein-Gordon equation with a potential term. So now let's just think about this. We have a wave equation. It's a Klein-Gordon equation with a potential term. The free part has a general solution which consists of packets traveling in mini superspace with this wave speed, if you like. You might think of one of the coordinates. You might think of alpha as time, if you like. But in any case, the solutions are spread infinitely over the mini superspace. And clearly, if I integrate the solution of the whole of mini superspace, it must diverge. So to think of mod psi squared as a probability is naive. Now, of course, in quantum gravity circles, this is very well known. I'm not saying anything new. People will say, well, you have to define probability in a different way. And, you know, what you're talking about here, what I've been criticizing is what's often called the naive Schrödinger interpretation, which was used a lot by Hawking and collaborators in the 80s, but I think is sort of widely regarded as naive. It's problematic. I mean, apart from the fact that psi squared is not normalizable, it's also timeless. Its probability distribution is timeless, and there's a long history of people trying to fix this by some sort of conditioning and so on. But at the end of the day, it fails because psi squared is not normalizable. It doesn't matter really how you jig this. Now, there's a common explanation, quantum gravity circle. The usual, probably the canonical explanation in canonical quantum gravity is that, well, this probability, here I've got a Gij and a matter field. This probability is naive because time is hidden in the three metric. So for example, in quantum cosmology, you might, for example, treat the scale factor as an effective time variable. Now, there's a long history of this going back to DeWitt and others in the 60s. It's still controversial. There are people, I understand, a lot of people in quantum gravity who think this is the right way to do it, but it remains controversial. Do you really recover standard quantum mechanics? You get issues, for example, what happens to time if you have a universe where the scale factor expands and recontracts? Does time stop and then reverse? Some people would reply to this, say, well, maybe time emerges only approximately in certain conditions, not fundamental. It's fair enough. There are people who take this view. I'm suggesting a new, so as I said, a common explanation. Psi squared is not normalizable because, well, you're being naive, that you have to, in a sense, extract an effective time parameter from the three metric and then discuss probabilities. I'd like to suggest here a different explanation, is that we sort of a little bit of a paradigm shift, if you like, that let's try to think this way, that in the deep quantum gravity regime, there is simply no such thing as the Born rule. And I want to try and convince you that this is a good idea. So the idea is that we can talk about probabilities, even time-dependent probabilities on superspace, but they're not tied to the Born rule. In fact, I'm going to argue that necessarily physical probabilities can never be equal to psi squared. And of course, because physical probabilities are normalizable and mod psi squared is not, they can never be equal. So quantum gravity is, in a certain sense, which I'm going to describe, in a perpetual state of non-equilibrium. And my claim is this is the true physical significance of the non-normalizable psi squared. Now, to make sense of this idea, we can look at the pilot wave theory of de Broglie and Bohm, which is a particular formulation of quantum mechanics, still not widely used, often misunderstood, but much more widely known than it used to be. Now, in this formulation of quantum mechanics, at least as I interpret it, and there's some controversy, the Born rule is not an axiom or law, but a state of statistical equilibrium, somewhat analogous to classical thermal equilibrium. This goes back to papers I wrote in the early 90s, my PhD thesis, 1992. Let me give a quick overview of this. So de Broglie's pilot wave theory, let me illustrate it. This was actually de Broglie's presentation at the 1927 Solvay conference. He presented the theory for a low energy many-body system of spinless particles. You have the usual Schrödinger equation. What's new, at the top on the right-hand side, you have an equation of motion for particle trajectories. The velocity of the nth particle is proportional to the gradient of the phase of the total wave function with respect to the coordinates of that particle. So you have a wave function in configuration space that is guide or a pilot wave. De Broglie thought of it as an actual wave in configuration space. It's not a probability wave. It is a wave that guides the motion of a single system. Now, for example, in the two-slit experiment, if I fire one particle at a screen, in de Broglie's pilot wave theory, there's a wave coming in, the usual wave that obeys the Schrödinger equation, and it guides the motion of a particle according to this law of motion. And the theory simply postulates this to be true, even if in practice we do not know the initial position of the particle. Okay, it's a deterministic theory of trajectories. Now, if we go back to the many-body theory, if we consider an ensemble of systems, an ensemble of similar many-body systems, it could be, just think of a theoretical ensemble of systems that happens to have the same wave function, but the initial configurations are different. So we have a distribution of configurations, which need not equal psi squared. It was shown by Bohm in 1952 in detail that if you assume that the initial distribution of configurations is equal to psi squared, then you recover quantum mechanics. And it so happens, as we'll now show, that if you assume that initial distribution, that distribution is preserved in time by the dynamics. Let's show a simple proof of that. Let's illustrate it for one particle. So I have my Schrödinger equation, which as usual implies a continuity equation for psi squared. And we're assuming, de Broglie assumes we also have particle trajectories, that each particle in the ensemble has a velocity given by the gradient of the phase divided by the mass. Now, if we assume that we have an ensemble of particles that has the same wave function but different initial positions, then I have a distribution of particle positions rho that necessarily evolves according to the continuity equation with a velocity field being by grad s over m. Now that continuity equation for rho is just a mathematical statement that each particle has a velocity given by grad s divided by m. Now if we compare that continuity equation with the continuity equation for psi squared that we got from the Schrödinger equation, we see they're the same partial differential equation. So if we have the same initial conditions, the solutions will be the same. So I have a simple theorem that if rho is initially psi squared, then rho is psi squared for all time. Now, this construction, so we call this quantum equilibrium. And this construction readily generalizes a general system. One might imagine, let's say I'm doing, this could be quantum field theory on a curved space-time background, as if I have a globally hyperbolic space-time, I have some time function, I can write a time-dependent Schrödinger equation for what would be a wave functional, and Q would be the configuration of fields on the space-like hypersurface. In any case, if I have a time-dependent Schrödinger equation, I can write down a velocity that's given by the Schrödinger current divided by psi squared. And so by construction, an ensemble of such systems would satisfy a continuity equation that is the same as a continuity equation for rho, and so on and so on, the same as the one particle case. And again, I show that the Born rule is preserved in time. So this is a general theorem. Now, going back to the example of the two-slit experiment, this means that if I had an ensemble of particles being fired at the screen, if the initial distribution of positions happens to equal psi squared, then I will get psi squared at the backstop, and I necessarily recover the two-slit interference pattern. On the other hand, and this is a point that people usually ignore in this field, is that if instead the initial distribution of particle positions is different from psi squared, then I will get deviations from quantum mechanics. So as an extreme example here, you might imagine if all of the particles started at the same point, shown with that red line, they would all land at the same point on the backstop. There would be no interference pattern, okay? So what this tells you, this simple example tells you that quantum theory is a special case of a wider physics, okay? There's quantum theory in the central region. There's a broader, a wider physics of non-equilibrium where rho is not equal to psi squared and where you get deviations of quantum mechanics. According to pilot wave theory, this wider physics can exist in principle. Now you may say, well, hang on a second. Experimentally, we always find quantum equilibrium. So here's an example of a particle in a two-dimensional box with a wave function that's a superposition of the first 16 energy states. If you prepare an ensemble of such systems and you measure the positions, you will always find this distribution of positions. Why? The usual view is that, well, rho equals psi squared is a law of nature. The view I'm pursuing here is that no, it's just an equilibrium distribution, a bit like thermal equilibrium. And if you ask, why do we always see this distribution? I would say that, well, because all of the particles that we can experiment with, all the particles that we see in the lab, have a long and complicated past history, and they have already relaxed. There's been a dynamical relaxation process to this state. Let me illustrate this. Some numerical simulations that were done 20 years ago. We have this two-dimensional box. The way at the bottom, I show the time evolution of the wave function. Sorry, the time evolution of psi squared according to the Schrödinger equation. Okay, it's a superposition of 16 energy modes. Psi squared sloshes around. This is a periodic system. So after some time, psi squared returns to its initial value. Now, if you start with a distribution rho that is different from psi squared, as you can see in the top left, and you let it evolve, you evolve the trajectories, so you can follow the time evolution of the density numerically. This is a numerical simulation. You find that over one cycle, rho approaches psi squared quite accurately. Now, I can show you just a quick look at sort of what the trajectories look like. The trajectories in this system are quite erratic, and they tend to explore the region. And this sort of similar simulations have been done for a number of cases. Let me just point out quickly, you can quantify the relaxation with a coarse-grained H function, which is minus the relative entropy of rho with respect to psi squared. The bars represent a coarse graining. This assumes there's no initial fine-grained structure in rho. you find an exponential, an approximate exponential decay of this H function. And this sort of thing has been extended to other, here's a similar simulation for a 2D oscillator with 25 modes. On the right-hand side, I've got the time evolution of psi squared with time going down the page. I've got initial density that's a Gaussian. You let it evolve, you see it rapidly approaches psi squared. And here there's a plot of the H function versus time. You see you get this approximate exponential decay. Okay, so now I'm supposed to be talking about quantum gravity, so this is just a quick background. The general message here is that, look, if you take pilot waves seriously, it's telling you that quantum theory is a special case of a wider physics. And that quantum theory in particular is the effective description of a state of statistical equilibrium. And we're stuck in that state now because of some past process of relaxation, which presumably happened a long time ago, close to the Big Bang. Now, if you follow these ideas, well, then it seems reasonable to expect that quantum theory could break down close to the Big Bang. There's been a lot of work done on this. I'm not going to talk about it here, but if you believe inflationary cosmology, then CMB anisotropies are ultimately generated by the Born rule applied to an inflaton field in the very early universe. So if you have violations of the Born rule for the inflaton field at early times, you can get anomalies in the CMB. Anomalies are reported in the data at large scales. There's been a detailed comparison with data made in this paper in 2019. There are some tantalizing hints. It's still all very uncertain. Even the existence of anomalies in the data is controversial. But still, that's the state of that. But the important message I want to get across is, according to this theory, we're trapped in the state of quantum equilibrium. And the natural question, is there a way to escape? All very well, interesting idea. Maybe in the very early universe there's non-equilibrium. Maybe there are traces in the CMB. Maybe there are not. But today in the lab, we always see the Born rule. Is there any way to escape from this? Is there any way that you might, for example, create non-equilibrium? Can we, smash particles very hard in the lab, try to knock them out of equilibrium? Well, it seems not, at least if you're in the regime of quantum systems on a classical space-time background with a time-dependent Schrödinger equation with a conserved Schrödinger current. It seems that no, doesn't matter what you do, the Born rule is preserved by the dynamics. You can think up any kind of clever scheme or rapidly changing, whatever. You always stuck, if you have the Born rule, you're stuck with it. Now that argument is true, at least in non-gravitational physics. Now finally, I can get to the topic of my talk, which is that quantum gravity may change the game. Perhaps in quantum gravity, things look quite different. Indeed, the main thrust of my talk is that everything I've just said about de Broglie-Bohm pilot wave theory and the Born rule, I think is correct if you're in the regime of quantum systems on a classical space-time background. If the actual space-time itself is quantized, then things are radically different. So let me sketch a little bit of pilot wave quantum gravity. There's, by the way, a very nice review article by Nelson Pinto Neto in 2021 published in Universe. But anyway, it goes back to the 90s. So the basic idea here, I've omitted a matter field. I'm just writing it for pure gravitation just to illustrate. But you have the Wheeler-DeWitt equation. There is a guidance equation for the three metric. There are trajectories for the three metric that essentially are proportional to the gradient of phase of the wave function. You can get this equation, if you like, by identifying the canonical momentum with the phase gradient. Anyway, this defines the dynamics of a single system. And this theory has actually been extensively applied to quantum cosmology by, for example, Nelson Pinto Neto and co-workers, Patrick Peter, a lot of other people working in Rio, also work by Stanov, Vink, going back to the early 90s. And in those papers, they study details of trajectories. For instance, demonstrating that you have fine singularity avoidance, that in an expanding universe you can avoid singularities at the beginning, this kind of thing. Properties of the trajectories have been studied. But people in that area tend not to talk about probabilities or ensembles. And in a way, you have a situation that's sort of opposite to textbook quantum mechanics. Textbook quantum mechanics, you can talk about probabilities, but not trajectories. Here, you can talk about, and people do talk about trajectories in quantum cosmology, but not probabilities. And the reason they don't talk about probabilities is, of course, because there's this problem that psi squared is not normalizable. So now I'd like to suggest a way forward is that just schematically for a general ensemble, we should take our dynamics of a single system, and then we should say, look, let's have an arbitrary ensemble with a distribution, a probability distribution P on superspace, that by construction will evolve according to this continuity equation, where we're assuming that each metric is following a trajectory with a certain velocity field given by gradient of the phase. And if I start off with an arbitrary distribution, it will evolve by this continuity equation by construction. And the claim is that unlike in the theory I described previously, this theory has no equilibrium state. Now, let's illustrate this with our model of quantum cosmology. If you do the usual polar decomposition of the wave function from the Wheeler-DeWitt equation here, you can obtain what I call a pseudo continuity equation. There's a factor A squared here just because of the peculiar structure of this mini superspace, but in effect, the usual psi squared density is replaced by A squared psi squared. But anyway, the point is now this density is non-normalizable as usual. But from this pseudo continuity equation, I can identify de Broglie velocities, which I can also get by just writing the condition that the canonical momentum is equal to the phase gradient. But anyway, what I've written so far, if I omit the bottom bit and just say, let's look at this, this is sort of standard de Broglie-Bohm quantum cosmology for a single system. I have the usual Wheeler-DeWitt equation, and I have equations for the trajectories. For trajectories. Okay, but what to do with probabilities? A squared psi squared is not normalizable. So what we can do, if I'm considering a theoretical ensemble of universes, I can say, well, by construction, if each element of the ensemble has this velocity field, then a general probability distribution must evolve by this continuity equation. Now, let's beware of the naive Schrödinger equation coming back to haunt us. Because P and A squared psi squared obey the same equations, and recall there's no T in psi, so these are the same partial differential equations, you might think that you have a state of quantum equilibrium. The probability is A squared psi squared, but it cannot be because a physical probability density is normalizable and the right-hand side is not. So my argument is there's no Born rule. We must have probabilities not equal to A squared psi squared always. Now, formally, you might look at our coarse-grained H function that we use to quantify relaxation. If the target measure is non-normalizable, then this has no lower bound. So I don't know if I mentioned before the H function that I defined before for a normalizable wave function, is bounded below by 0. So as you get relaxation, it starts off bigger than 0 and it relaxes exponentially, and it's bounded below by 0. But anyway, here's no lower bound. Equilibrium can never be reached. In fact, I have a paper coming out soon with Aditya Kandhadai where we perform numerical simulations in that mini superspace model, and we show how, in fact, you don't get relaxation, even locally, you don't get relaxation. So the message is that quantum gravity is in perpetual non-equilibrium. So now there's an immediate question. Well, if that's true, if at the Planck scale there's no such thing as the Born rule, how on earth are you going to recover the Born rule for example, quantum systems on a classical curved background, or for quantum systems in the lab? Now, the answer is that while the Born rule can emerge in the semi-classical regime by the usual process of relaxation, because in the semi-classical regime, you have the usual time-dependent Schrödinger equation, for which, as you know, extensive studies have shown, you do get relaxation. So let me just sketch for you. This is standard, pretty much standard stuff, semi-classical. So solution to the Wheeler-DeWitt equation. I write it approximately. I have a WKB solution for the classical background, and there's an effective wave function, little psi, for my quantum field propagating on that background. And the little psi depends on the 3 metric, but the 3 metric is approximately classical, and it's a function of time. So I can write an effective time-dependent wave function for the quantum field, and I can define an effective Schrödinger equation. For example, there's a nice paper by Kiefer and Singh back in 1991 discusses all this. Now, once I've got the effective Schrödinger equation with a normalizable psi, then I just have the usual thing that I talked about earlier in the talk. You get conventional quantum relaxation, which has also been discussed. I should have mentioned the kind of relaxation I showed you for the 2D oscillator has been discussed for a quantum field on a background expanding space in that work that I talked about, involving the CMB, corrections to inflationary cosmology. So, you know, numerical simulations have been done for a quantum field propagating on an expanding classical background, and you find the usual relaxation, at least at short wavelengths. Super Hubble wavelengths, you get some retardation. That's why we predict corrections to the CMB at large scales. That's a topic for another talk. But anyway, at least at sub-Hubble scales, we expect the usual quantum relaxation. So the expectation here is that while you will begin out of equilibrium in the deep quantum gravity regime, as you emerge into the semi-classical regime, as the universe expands, in the early universe, you will get relaxation to the Born rule in the usual way. So despite the claim that that fundamentally there's no such thing as the Born rule in the deep quantum gravity regime, nevertheless, we have an explanation for why we see the Born rule in the semi-classical regime. The explanation is via this quantum relaxation process that can take place for quantum systems on a classical space-time background. Now I have 10 minutes left. So now you might say, okay, that's all very well. Maybe there was no Born rule in the very beginning in the deep Planck regime, but still you're expecting to emerge into the semi-classical regime in the early universe. You're going to get quickly relaxation. Again, today, 14 billion years later, we're again stuck forever in quantum equilibrium, no? So perhaps not. Now, let me just pause a moment and reiterate what I said at the beginning. Remember the 3 main points I want to get across. One is that there's no such thing as the Born rule at the fundamental level of quantum gravity. 2 is that the Born rule emerges only in the semi-classical regime. I think those 2 arguments are quite strong if you assume canonical quantum gravity and you assume that the de Broglie formulation of quantum gravity. I think in that theoretical structure, these arguments are quite strong. The third claim is that there could be corrections to the semi-classical regime in which the Born rule is unstable. This is a bit more, I think, open to question in a particular way that I'll describe. So the idea is that tiny corrections to the Schrödinger equation can make the Born rule unstable. Why is that? So going back to the paper I mentioned by Kiefer and Singh, 1991, if you perform a semi-classical expansion, the higher order terms, you get quantum gravitational corrections to the Schrödinger equation, and some of those corrections are non-Hermitian. And for a long time, people have not known what to do with these terms. They just ignore them. Of course, they're inconsistent with standard quantum mechanics, but they are consistent with pilot wave theory. If you take these non-Hermitian terms seriously, they generate a small instability of the Born rule. Now, this is where I say, I think this is open to question. there's a bit of a controversy in the literature. Some people think that, look, these non-Hermitian terms, that they're an artifact. You need to eliminate them by maybe by redefining the wave function some way, or by performing the semiclassical expansion a different way. And maybe that's right. Maybe these non-Hermitian terms are an artifact, in which case this instability will not exist. But I think it's worth exploring the idea that perhaps they're not artifacts, in particular because if you take pilot wave theory seriously, there's no problem with non-Hermitian terms. Let me just quickly describe non-Hermitian corrections. Just schematically look like this. So I've got a quantum field on a classical space-time background. There's the usual field Hamiltonian, and there are small corrections. They're both Hermitian and non-Hermitian corrections. And there's more recent work in quantum cosmology by Brizuela, Kiefer, and Kramer. Let me say explicitly, if I just sketch for you a little bit what Kiefer and Singh, what Kiefer and Singh talked about in 1991, schematically, they've got a semi-classical expansion of the Wheeler-DeWitt wave functional, and they obtain a corrected Schrödinger equation for the quantum field on the classical background that looks like this. The emission correction term is proportional to the square of, so h hat subscript phi is the usual Hamiltonian density for the quantum field. So the Hermitian correction is proportional to the square of that Hamiltonian. And there's a non-Hermitian correction that is proportional to the time, proportional to the phase gradient, or in fact the bubble time derivative of the Hamiltonian, of the field Hamiltonian, which of course is not, its time derivative is non-zero because you're on a time-dependent classical background. Now, let me just sketch for you how pilot wave theory can handle these terms. We're saying schematically that the semi-classical expansion of the Wheeler-DeWitt equation gives you something like this. You have a time-dependent Schrödinger equation for your quantum field. H1 is, sorry, both H1 and H2 are Hermitian. So I've got it, the Hamiltonian has a Hermitian and a non-Hermitian part. I should mention that if you do the de Broglie-Bohm version of the semi-classical expansion, you also have to look at the semi-classical expansion for the de Broglie guidance equation that defines the trajectories. And I've done that in detail in the papers that appeared 2 years ago and 4 years ago. Anyway, if you go through the semi-classical expansion of the de Broglie guidance equation, you find that, okay, while the Schrödinger equation gets this non-Hermitian correction, the velocity field coming from the de Broglie equation is still given by the standard quantum current that's associated with the Hermitian part of the Hamiltonian. So in other words, it's as if the guidance equation is not really affected. It's still given by the usual formula. So what this means is if I write down my continuity equation for an arbitrary density rho, it has a velocity field given by the standard quantum current. But psi squared, because the Schrödinger equation has a non-Hermitian term, the continuity equation for psi squared has a source term, has an effective source. So, you know, the normal continuity equation S would be 0. Here, S depends on this non-Hermitian part, H2. So the two continuity equations no longer match. Now, you may remember the argument I gave at the very beginning of this talk. Usually in pilot wave theory, the continuity equation for rho and the continuity equation for psi squared, they're the same partial differential equation. So if rho is initially psi squared, they remain equal. Here, because the continuity equations don't match, an initial Born rule density can evolve to a non-Born rule density, and you can estimate the time scale for this process that goes inversely as the modulus of the expectation value of this non-Hermitian term H2. Now, could such effects be observed? The $1,000,000 question, or the €1,000,000 question, or the £1,000,000 British pound question. Anyway, quick look at cosmology in the CMB. In the paper I mentioned by Kiefer et al. 2016, they looked at scalar perturbations on de Sitter space. And they found the corrected Schrödinger equation looks like this. You see, again, you've got the Hermitian term. So HK is the usual Hamiltonian for a, sorry, this is a field mode. So I've got a certain mode of a quantum field on de Sitter space, and HK is the usual quantum Hamiltonian. There's a Hermitian correction that's proportional to the square of HK, and then there's a non-Hermitian correction that, again, you've got a time derivative of the Hamiltonian with a factor 1 over a cubed, where a is a scale factor, of course. Now, Kiefer et al. Consider only the Hermitian term because, you know, the non-Hermitian term is inconsistent with standard quantum mechanics. They find a tiny correction, a predicted tiny correction to the power spectrum of order 10 to the minus 10, which I think that's a fractional correction. Anyway, I should know that. But anyway, far too small to see in the CMB. There's a paper, I have a long paper on the archive where I do a similar calculation or estimates, a rough estimate really, trying to include the non-Hermitian term, and you find you get a similar tiny correction, again, just far too small to see. So in principle, this correction would be there, but far, far too small to see. Perhaps a bit more encouraging is looking at an evaporating black hole. Again, something that was discussed in a paper by Kiefer and collaborators in 1994. You've got a quantum field in the space-time of an evaporating Schwarzschild black hole, and they argued that in the semiclassical regime, the field mode has a non-Hermitian correction that looks like this, where kappa is a numerical factor. M is the mass of the black hole at time t, and of course the mass is decreasing with time, and HK is just the field mode Hamiltonian for this quantum field in this background space-time. They argued that this may, in that paper, they argued this may have something to do with resolving the problem of information loss. That's another story. From a pilot wave perspective, we can discuss the time evolution of the quantum field on this background. And there's no problem discussing the time evolution of a probability density. The probability will be conserved by construction, but the Born rule will be unstable. So what this means is, now I only have a rough estimate so far, estimate the time scale. The time scale for this process goes as a fifth power of the mass over the Planck mass. The effect is significant only when the mass approaches the Planck mass. This suggests that in the very final burst of Hawking radiation, the radiation will break the Born rule. The details, I'm trying to do some work to get some more details of how big the effect might be and so on. It's still an early stage, I'm afraid. But anyway, the estimate of the time scale suggests that the final burst could break the Born rule. Now, it so happens that, of course, experimentally, we are in effect looking for exploding primordial black holes. Various experiments, for example, the Fermi satellite is scanning the skies for anomalies in the X-ray, gamma ray region, looking for disintegrating dark matter, for example. It could happen tomorrow that we identify hard X-rays coming from exploding primordial black holes, which some people think are a significant component of dark matter in our galaxy. So one could imagine that if we find, sorry, gamma rays, sorry, the hard X-rays, it's for annihilating dark matter. Anyway, sorry, gamma ray, let's say gamma ray region. If tomorrow we find gamma rays coming from exploding primordial black holes, I would suggest, well, let's try to do some kind of test of the Born rule for these gamma rays. How to do a two-slit experiment with gamma rays would be a challenge, but something like a test of the Born rule. In fact, I have papers about how looking at anomalous polarization probabilities is actually a more practical and more general test of the Born rule. So this would be probably the way to do it for gamma rays. Look at polarization probabilities. The polarization probability varies with angle in a certain way as you rotate the angle of your polarizer. It's a general prediction of quantum mechanics. Anyway, the difference, no time for that here. But it so happens also there is a German satellite that was supposed to have launched last year. I'm not quite sure what's happened. It's called the Quick 3 satellite mission. And their aim is to test the Born rule in space. They have an interferometer. I think it's a 3-path interferometer on board. And they have a quantum sort of light source on board. They want to test the Born rule in space for single photons from their onboard source as a sort of proof of principle of testing the Born rule in space. Once such a system is up and running, I might add that they do cite my paper as one of their motivations, that it's, you know, there's motivation for testing the Born rule. Anyway, once such an experiment was up and running, if we did discover gamma rays coming from primordial black holes, then you might, instead of having photons from their onboard photon source, it's an optical photon source, we could perhaps have these gamma rays impinge on their interferometer. Anyway, something possibly for the future. I might add that the indications from this estimate about what would happen with the Born rule and exploding primordial black hole, you would only expect to see significant effects in the very final burst. How you would identify that in an black hole explosion, I don't know. It would be extremely difficult because it would only be the very final burst. So this is at the moment in the in principle stage of discussion. How practical it might be, I'm not quite sure. But anyway, let me just draw my conclusions. I think I've just 2 or 3 minutes over time. Let me just draw my conclusions. Is that quantum gravity is fundamentally a non-equilibrium theory, at least from the point of view of the Broglie-Bohm formulation of quantum mechanics. There's no Born rule at the fundamental level. We find relaxation to the usual Born rule only in the semi-classical regime, so we still explain what we see in the lab. A bit more open to question, more controversially, there are corrections to the semi-classical regime, and some of the terms are non-Hermitian. In pilot wave theory, there's no problem with such corrections. They yield a small instability of the Born rule. These latter effects are very small, except in the final burst of an evaporating black hole, at least according to the rough estimates. Possibly this might be observed one day. If I may be forgiven for taking a final 30 seconds, a small advertisement. I have a popular book coming out this summer, and here is a preview of the cover. There we are. Thank you so much. Thank you.
Thank you very much for your inspiring talk.
Thank you.
Now we have some time for questions.
How much is the book going to be? I'm not sure. How much will it cost? I don't know.
So, do we have some comments? Remarks?
Can I have a very short and naive question?
Sure.
First, hi, Anthony.
That sounds like Patrick Peter to me.
Yeah, that's me.
Hello,
indeed.
Patrick. How are you?
Fine, and you?
I hope the weather is better in Paris than in London. That's all I can say.
Not really. Anyway,
okay.
We can discuss that later.
All right.
Wondering, when you mentioned that the functional is not normalizable in quantum gravity,
yes.
Would this conclusion, that may be very naive, but would this conclusion also hold if I were to limit the range of variation of all the variables and assume that all the variables vary in compact spaces? Because it seems to be because you're having integrals
well,
which are
yes.
unbounded, but then
Well,
let's say we do
yes.
that with the volume. We assume that the volume is compact.
Yeah. Yes. No. Right. No. That's right.
Could be
Yes.
another
I
of
mean,
your
now
consequences that time is bounded.
remember the degrees of freedom we're talking about. We've got, for example, in the quantum cosmology, we've got a scalar field, we've got the scale factor. I mean, if we said, I mean, you might imagine that maybe in a, in a closed universe, maybe the scale factor would be bounded between 0 and some maximum value. But then the quantum field, why would its value be bounded? I mean, I think it's a fair point. It's a fair point. I mean, you're basically, the answer is yes, you're right. If you had a good way of making the configuration space finite volume, then this problem would go away. And maybe there's a way to do that. I've not seen anyone try to do that. I would have thought it's going to be problematic, but fair enough. Fair enough.
Okay, thanks.
Okay.
Okay. Further questions? Comments? Remarks? I can't hear any, so let us thank the speaker again.
Thank you. I
Thank you
seem to
very
have
much.
stunned everybody into silence. Well, there we go. I don't know if that's a good sign or a bad sign, but never mind. Thank you so much.
You're welcome. So